Hi everyone, and thank you for listening to this presentation. My colleagues and I from Utrecht University have investigated medical dialogue summarization for automated reporting in healthcare. First, let me introduce myself. So the voice you're listening to belongs to this phase. My name is Sabine Molenaar and I have a background in information science and business informatics. My research interest is in dialogue summarization and automated reporting, and this research was executed in the context of the Care to Report research program. I want to start off with the problem statement because the administrative burden in healthcare is actually a well-known problem in many disciplines. For example, first-year residents in the US spend on average more time with the electronic medical record than actually helping patients. The electronic medical record was introduced to help solve issues with administration, and while it has several benefits, such as improved understanding by patients and a positive communication experience, it also has some concerns. For example, patients worry that doctors might get distracted by their computers, and an average 32% of the time is spent on computer interactions by the doctors. And this leads to a potential loss of nonverbal communication when speaking with a patient. Since the problem is well known, research has been done before. Several attempts have been made at generating healthcare documents automatically. An example is dictation. This is a popular approach in studies, but is rarely used in practice due to the disruption of the normal way of working for doctors, the lack of support by hospitals, and any financial constraints it might include. Other solutions are creating transcriptions of the full doctor-patient conversation, but doctors usually only write a report that is a summary of the conversation and not the conversation as a whole. It has been shown that textual summaries can be generated, such as in the Baby Talk project, but in their results it was shown that human expert texts were still superior to the ones that were generated. Artificial intelligence that uses both natural language processing and machine learning in healthcare can be used to enrich medical data, but there is a risk of underrepresentation of rare occurrences and also a lack of transparency towards patients and doctors. In order to facilitate automated reporting, we have developed the dialogue summarization pipeline. It can be defined as a series of NLP and/or AI-enabled computational components which transform output from one system into input for another system. For example, the left system could be some kind of recording device for audio, and then this audio is given to the pipeline. The pipeline will then generate a report which can be used as input for another system, for example, the electronic medical record. The dialogue summarization pipeline looks like this. At first, audio is provided to the system and a speech transcription will be made of the conversation. Then, based on this transcription, triples can be extracted. Triples can be seen as two concepts with a relationship between them. So, for example, a patient can have an earache. Since we are not medical professionals, we use a clinical guideline library for existing knowledge. Using this library, ontology can be created. This ontology creates information related to diseases, diagnoses, and symptoms. For example, the patient history section of the clinical guideline for ear infection mentions that the general practitioner should ask the patient about whether they have any pain, itching, or suffer from hearing loss. The ontology thus contains information such as ear has symptom pain and ear has symptom itch in line with the clinical guideline. We compare the extracted triples to the triples that are contained in the ontology. If there is a match, it can be considered relevant information for this consultation. All the matched triples, or the relevant information, can be stored in the patient medical graph. This is a summary of the anatomy, symptoms, observations, and treatments related to a patient. All the relevant information will be used to generate a report. For this, we use the Medical Convention Guideline Library, because in the Netherlands, general practitioners use the SOUP format to create their reports. The SOUP format basically includes a subjective, which is the story of the patient, the objective, any examinations or observations made by the doctor, and the evaluation, which is the diagnosis that follows, and finally the plan, which includes the treatment, which could either be some medication or a referral, or any kind of other treatment they may think of. To improve the quality of the generated reports, we use quality measurements to determine where we can improve in the pipeline. We distinguish three types of quality measurements. The first is the pipeline quality, which means comparing the output of the entire pipeline to a golden standard, ground truth, or any real values, such as example reports written by doctors. The second is component quality. We compare the output of one component in the pipeline to a golden standard or ground truth, and also apply generic metrics to determine what the quality of this component is. For example, for the speech transcription component, we might want to determine what the word error rate is when this transcription is compared to a transcription written by a human. Finally, we have the error propagation quality measurement. We compare the output of the components to the output of the pipeline, and the differences denote the errors that are introduced in each component. The quality measurements can be visualized as follows. The pipeline quality covers all the components and compares the final output to some golden standard or ground truth. The component quality is related to specific components in the pipeline, so for example speech transcription or triple extraction. Like I said, for speech transcription you might want to determine the word error rate, and for triple extraction you might want to determine how many unique triples there are. Finally, there is error propagation, which can be done for any component in the pipeline. For error propagation, we compare the generated output to a ground truth and then determine which items or information went missing. And then for each component, we can determine whether they are the culprit of the missing information. To determine the quality of the developed pipeline, we have generated 8 reports from audio of doctor-patient consultations concerning otitis externa, or ear infection. This table provides an overview of the quality of the generated reports. We show the precision, recall, and F1 scores, as well as the number of false positives included in each report. The average precision is above half, but the average recall is quite low. Report 6, which happens to be the longest consultation, scored poorly on all fronts, and included only false positives, so only incorrect information. False positives are present in nearly all reports, and some are due to negations. For example, a patient says, "I don't want antibiotics," but antibiotics are included in the report. Our next challenge is to ensure that the system can recognize negations in order to provide correct information and not include wrong treatments. Report 3, however, scored well both precision and recall and has an F1 score of above half. Reports 5 and 8 even have a perfect precision score of 1. We use off-the-shelf software to extract triples, and on average more than 1,000 triples are extracted from each transcription. However, only between 0.9% and 2.1% of these triples are of sufficient quality. Low quality triples are incomplete. For example, you have triples that contain some kind of placeholder, such as event 1. Event 1 may then point to a specific occurrence in the consultation, but is not included in words. Another challenge is implementing video input. Using video input, we can enhance text that includes gestures. For example, when a patient says, "This ear hurts," we can see whether he's indicating the left or right ear. We found that all matched triples are included in the report because they are of sufficient quality. However, some triples are incorrectly categorized. For example, if there's a mention of medication, they always end up in the plan, even though they might be part of patient history, which is part of the subjective. Another challenge is recognizing verb tense. Using the verb tense, we can distinguish between used and prescribed medication. In order to determine the error propagation, we have compared the information included in the generated reports to a golden standard, so reports written by a general practitioner. Missing information was traced backwards to the last mention in the components. The majority of the missing information could be found in the extracted triples, but they were part of the triples that were of poor quality and could not be used. Some information was only implicitly mentioned in the transcriptions or never mentioned at all. Based on this, we know that the triple quality needs to be improved in order to include more relevant information. In addition, implicit information needs to be extracted. An example of implicit information is when a patient says they had a terrible experience with a certain medication, but they never literally say no to the medication. Finally, I would like to share some limitations, directions for future research, and conclusions. For the validity threats and limitations, more consultations are needed for a more reliable assessment, because only 8 reports were generated. In addition, we should include stylistic variations. This means that we include reports written by various general practitioners. So far, we've only compared our outputs to a report written by only one person. Finally, we need to extract implicit information, such as questions and answers that are split between turns in the conversation, colloquialism synonyms that are not in our list of synonyms and words, and demonstrative pronouns and pointing and gestures that cannot be identified by just audio. In the near future, we would like to acquire more reports and transcriptions for experimentation and a more thorough error propagation analysis. We also wish to include a golden standard that includes written reports by multiple general practitioners. And so far, we've only included support for ear infection, but would like to support other diseases as well. We would also like to implement relevance filtering to reduce the amount of unused text. As we've seen before, the longest transcription scored quite poorly. We would also like to implement video and sensors to complement the information that can be extracted from audio. Based on this research, we can draw 3 conclusions. First, there is evidence that medical dialogue summarization is achievable. Second, the relevance of the reports generated by the proof of concept is acceptable. but the pipeline structure requires optimization to improve the completeness of the generated reports. This concludes the presentation. I want to thank you for listening, and if I've piqued your interest, I would also like to invite you to read the paper.